तो हमारा जो टॉपिक है, जैसा कि आप लोग जानते हैं, आज हम इस टॉपिक को क्लियर करेंगे टेम्परेचर वाले पे।
You have learned that air that is
तो देखो, ये जो टेम्परेचर लैप्स रेट के बारे में जो लिखा है, देखो, इन दिस लैब विल बी यूजिंग द टर्म्स एयर पार्शियल। ठीक है ना। देखो, इसके अंदर क्या है कि जो टेम्परेचर की जो बातें चल रही थी आप लोगों का, जो लैप्स रेट एंड स्टेबिलिटी की बात है, जैसा कि ऑलरेडी आप लोग जान चुके हैं, इसमें रेफर्स किया जाता है एटमॉस्फेयर के जितने भी रिलेटिव यूनिफॉर्म होते हैं उसके बारे में बताया जाता है कि किस तरीके से इसका वेरिएशन होता है और किस तरीके से ये स्टेबिलिटी लेता है। जैसा कि मैंने एक चीज़ बताया था आप लोगों को, पहले ये देखिए क्या है, इसके बारे में जान लीजिए कि दिस रेफर्स टू अ पार्ट ऑफ एटमॉस्फेयर दैट्स हैज़ अ रिलेटिवली यूनिफॉर्म टेम्परेचर एंड रिलेटिव ह्यूमिडिटी एंड कैन बी कंसिडर्ड पार्सल। ओके, तो देखो इसमें क्या है कि जो टेम्परेचर का रेट है, जो रेटिंग होती है, उसमें आपको क्या देखने को मिलता है कि दिन के टाइम में वो काफ़ी बड़ा होता है और टेम्परेचर दिन में रेस पे रहता है और नाइट में आपका डाउन रहता है। लेकिन ये डिपेंड किससे करता है, किससे रिलेटिव है, तो ये आपके ह्यूमिडिटी के ऊपर रिलेटिव है। कैसे कि नंबर ऑफ पॉपुलेशन डिसाइड करता है, नंबर ऑफ व्हीकल्स, नंबर ऑफ यूजेस, नंबर ऑफ एनी अदर पार्टिकल्स। ठीक है ना। क्योंकि कोई भी अन्य पदार्थ होगा जिसका कोई मतलब समझ लो एक तरीके से तुम्हारा वर्क अगर एबिलिटी ना हो चीज़ों पर, तो जो चीज़ें आपको दिखेंगी वो ये दिखेगी कि जिस तरीके से हमारा जो टेम्परेचर है, ठीक है, हमारा जो टेम्परेचर है दिन के टाइम में, जो सूर्य के तपन से, जो गर्मी से, हीट से जो अर्थ सरफेस गर्म हो जाता है, वो जो हम लोग व्हीकल्स यूज़ करते हैं या ट्रांसपोर्टेशन इमिशन में जितने भी यूज़ होने वाले व्हीकल्स हैं, ठीक है, जितने भी यूज़ होने वाले व्हीकल्स हैं उनके टर्म में किस तरीके से ये चीज़ें बढ़ती ही जाती हैं और ये कहीं ना कहीं अफेक्ट होता है, क्योंकि ये पार्शियली होता है। पार्शियली रेफर्स तो है ही है, प्लस पार्शियली जो है आपका बढ़ते जाता है। कंसिडर करना पड़ता है इन सभी चीज़ों को, अदरवाइज क्या होता है कि कहीं पे टेम्परेचर उसके एटमॉस्फेयर के हिसाब से डाउन रहेगा, कहीं अप रहेगा, लेकिन टेम्परेचर रेंज पे ही रहेगा। फ्लक्चुएशन रहते हैं, वेरिएशंस रहते हैं टेम्परेचर में, आर्द्रताओं के कारण। अगर वैली है, कोई घाटी है या कोई नदी है या कुछ भी है, तो वहाँ पे वेरिएशंस रहेंगे, ठीक है। बट अगर आप उन वैलीज या घाटी से दूर हो, उन वैलीज या घाटी से दूर हो, तो फिर क्या है, आपका जो भी सिनेरियो बनता है, जो भी सिनेरियो बनता है वो उस तरीके से ना होकर के किसी अलग पॉइंट ऑफ व्यू से रहेगा। इतनी चीज़ें तो स्पष्ट रूप से जायज़ है, आपको भी पता है, इतनी चीज़ें स्पष्ट रूप से जायज़ है कि किस तरीके से आपका रहेगा। ठीक है ना। अब क्या है, अगर हम बात करें, ठीक है, कि जो भी फंडामेंटल डाटा है, ठीक है, जो भी फंडामेंटल डाटा है उसको एडॉप्ट करें तो कैसे करें। ठीक है, क्या करें कि वो अडॉप्ट हो जाए, क्या ना करें कि अडॉप्ट ना हो। तो देखो सबसे बड़ी बात ये है कि जो भी टेम्परेचर हमें मिल रहा है, जो भी चीज़ें हैं इस रेट पर, पहली बात वो गैस लॉ के ऊपर डिपेंड करता है। जो भी गैस लॉ होते हैं आपके फ्रेमवर्क, अगर मैं बताऊं गैस लॉ, ठीक है ना, गैस लॉ के ऊपर वो डिपेंड करता है। फ्रॉम लास्ट वीक लैब वी लर्न द फॉलोइंग अबाउट गैसेस। लोगों ने पिछले बारे में पढ़ा था गैस के बारे में। क्या मैंने बताया था पिछले सप्ताह में कि जब गैस होती है, गैस उसको अगर हम कॉम्प्रेस करते हैं तो उसके अंदर देखो मॉलिक्यूल्स दूर दूर होते हैं। क्या होते हैं? दूर दूर होते हैं। दूर दूर होने के कारण जो है वो ठंडे होते हैं, उनके अंदर हीट नहीं होती। लेकिन जैसे कंप्रेस करते हैं उसके पे प्रेशर पड़ता है, वो गर्म होते जाते हैं, वो मॉलिक्यूल्स जो है वो गर्म होते जाते हैं। मैंने क्या बताया था कि लोअर लोअर प्रेशर allow gas to expand and higher pressures result in compression of gases. That is the difference between lower pressure and higher pressure. Clear है? गैस दैट एक्सपेंड विथ कूल, अगर वो दूर दूर है तो वो कूल रहेंगे, कूल के साथ रहेंगे। गैस अगर कंप्रेस करेंगे, गैस इज द कंप्रेस विल वार्म। अगर हम कंप्रेस कर रहे हैं तो वार्म होगा। दिस इज द मैटर ऑफ गैसियस लॉ। we will use we will use the physical process to better understand the behavior of air parcel and result weather process। क्लियर है? उसके बिहेवियर के बारे में बता रहे हैं। अगर लैप्स रेट की बात करें, इफ आई टॉक अबाउट लैप्स रेट, तो वी हैव अ ग्राफ। एज्यूम वी हैव अ ग्राफ। First, if we consider the horizontal line and second the vertical line, the vertical line is to be a scaling of 0 to 5,000, 10,000, 15,000, 20,000, 25,000, 30,000, 35,000, right? Then horizontal plane is to be a scaling of -70, -60, 50, माइनस में ही ये सारे रहेंगे, -40 करते करते 0 + 10, and we did vertical atmosphere profile in 15,000, okay, level, vertical scaling in 15,000. So the graph will be increase and reduce because yesterday मैंने आपसे यही बोला कि जो हजार हजार का है, किसके बारे में बोला था? 1000, 2000, 3000, 4000, किसके बारे में बताया मैंने? ये जो हजार हजार के हैं, उन हजार हजार में आपको देखने को क्या मिल रहा है? एडियाबैटिक प्रोसेस and dry adiabatic process and wet adiabatic process. What is adiabatic? And also time in variation for our climate, like as daytime and night time. Which process to convert the temperature? How? How can it possible? The temperature will be increase and decrease. It is possible and it is a possible. So what is the process of our nature? Right? तो ये चीजें जो है आपको समझनी होंगी और समझे भी हैं। Got it? तो होता क्या है इसमें कि जो आपकी टेम्परेचर इन्वर्जन है वो भी डिपेंड करता है। This describe how temperature varies with altitude and describe the lapse rate. Keep in mind, altitude vertical displacement is to be equal to the altitude. Okay, and describe the lapse rate. Lapse rate, it means when the temperature is down, when the temperature is up, raise and down, raise and up, ठीक है ना? There are three types of lapse rate. If I talk about lapse rate, there are three types of lapse rate. First, देखिए कहने को ये है कि जो लैप्स रेट है, ठीक है, तीन तरीके के हैं. पहला है ELR. व्हाट? ELR lapse rate. Okay, ELR lapse rate. What is the full form? ELR, environmental lapse rate. ठीक, environmental lapse rate. Again, ELR. The ELR is what we do last week. मैंने बताया था. Describe how actual temperature varies with altitude, and this changes from day to day or even over the course of the day. Okay, and if I talk about dry adiabatic lapse rate, what is dry adiabatic lapse rate? Dry adiabatic lapse rate. Adiabatic means that the air process like rising air does not exchange heat with surrounding, and dry adiabatic lapse rate is the rate of dry air will cool as it rises in the atmosphere. This is the fixed rate, like 5.5 Fahrenheit per 1000 feet or 10 degrees Celsius per 1000 meter. Got it? What is bed adiabatic lapse rate? We also called most adiabatic lapse rate or saturated adiabatic lapse rate. मतलब कहने को क्या है कि जो कि मैंने पहला बताया था कि एडियाबेटिक जो है आपका वो मोस्ट है, मॉइस्चर लेता है, उसको सैचुरेटेड भी मान सकते हैं. क्या? सैचुरेटेड भी माना जाता है. क्लियर है? अब एडियाबेटिक का जो लैप्स रेट है वो आप देखिए, वो क्या है कि we will use to 0.7 and 5.5 per 1000 feet. This is help describe the moving up or down of inside of air cloud where RH 100% is. Okay, 100% RH. With wet adiabatic lapse rate is smaller because heat is released during a condensations of decreasing the rate of temperature change. Okay. Example, the environmental lapse rate is 3.8 F per 1000 feet. If ground temperature is 68 F or यानी Fahrenheit, what will temperature be at 5400 feet? So we have a formula. We take a formula. Temperature is equal to elevation into lapse rate. Temperature, how many elevation feet? Elevation and vertical displacement 5400 feet. And what is the temperature lapse rate? The temperature lapse rate 3.8 Fahrenheit upon 1000 FT. ठीक है? टोटल काटने पर पीटने पर आपको यही मिलेगा 220.5 फ़ारेनहाइट. तो व्हाट इज द एक्चुअल फ़ारेनहाइट? वी हैव आल्सो ground temperature 68 Fahrenheit. Basically, you will be take your 68 Fahrenheit and result Fahrenheit, resultant Fahrenheit 220.5, and given the data of temperature ground, given data ground temperature 68 Fahrenheit. Basically, you will be take a calculation. The calculation is to be 68 minus 20.5, and your answer is to be as to 47.5 Fahrenheit. Okay, and dry adiabatic. ड्राई एडियाबैटिक की अगर बात करूं तो मैं ड्राई एडियाबैटिक जैसा मान लो एक बैलून है, ठीक है, जो कि क्लासरूम में है और 70 फ़ारेनहाइट डिग्री है, ठीक है। अब इसका फार्मूला क्या होगा? तो देखो 5.4 टेम्परेचर ऑलरेडी दिया हुआ है, मान लिया वही हो गया आपका, टेम्परेचर मैंने दे दिया, हाइट वही रख लिया 5400। तो क्या है 5.4 बटे 10 1000 करोगे और गुणे 5400 20 कर दोगे तो वही तुम्हारा 29 के नियर अबाउट आएगा। तो इस तरीके की चीज़ें हैं जो आपको प्रोसेस में लानी रहती है। वेट एडियाबेटिक समझ ही रहे हो, तो ये जो है फार्मूले आप याद कर लीजिएगा ताकि आपको सुटेबल रहे। ऐसा ना हो कि आप लगाते जाएं और देखो टेम्परेचर का, देखो बहुत सिंपल सा रूल बता दे रहा हूँ, टेम्परेचर का फार्मूला ही यही होता है। अब बहुत ईजी गोइंग है। अब उसमें आता है टेम्परेचर एज क्रिस्ट, ठीक है ना, टेम्परेचर एज क्रिस्ट आता है। एक टेम्परेचर होगा तो जो कि नॉर्मल है, और टेम्परेचर ऑफ पार्सल ये भी देखना है। टेम्परेचर तीन चीज़ें, टेम्परेचर लैप्स रेट में टेम्परेचर देखना, टेम्परेचर पार्सल देखना, टेम्परेचर एट क्रिस्ट देखना। तो ये चीज़ें जो है आप लोगों को समझना होगा, ठीक है। और इसके फार्मूले जो हैं आपको याद करने होंगे, कर लीजिएगा, आपको इसके सॉल्व हो जाएंगे। वैसे तो थ्योरेटिकल है, पूछता तो नहीं है इतना, लेकिन तब भी जो है आप लोग जो है उस चीज़ को याद कर लीजिएगा ताकि आने वाले टाइम में आपको अच्छे से ये चीज़ें पता चल सके। और भी कई सारे प्रोसेस हैं, ठीक है। और मैं सोच रहा हूँ कि एक स्लाइड में चला दूँ आप लोगों के लिए ताकि जो है आपको ये चीज़ें समझ में आ जाए अच्छे से, और यही लैप्स रेट के बारे में होगा। तो इसको आप सुन लीजिए, उस हिसाब से आपको समझ में आएगा। जहाँ ना समझ में आया आप हमको बताइएगा। तो मैं प्ले करने जा रहा हूँ इस स्लाइड को, ठीक है।
In this video, I'd like to talk a little.
स्लाइड
Let's get right to it here. The week before, we did some experiments about gas laws, and what we learned from the gas laws were some of the following things. One is we learned that with lower pressure, gases will expand. At higher pressures, when you subject gases to higher pressures, that results in compression of the gas, and that makes kind of sense. Now, when gases expand, when they're exposed to that lower pressure, they will also cool. There are fewer interactions and the temperature will drop. And when you have compression of gases, that will result in an increase in temperature. And these will be important concepts when we start talking about lapse rate and stability of the atmosphere. So we'll be using these physical processes to better understand the behavior of air parcels and resulting weather processes. So last week we did lapse rates. We did vertical atmospheric profiles. This is an example from Salem, April 15th, 2013, that shows temperature on the horizontal axis and altitude in meters. And you can see it varies up to about 5,000 meters or so, and then starts steepening and heating. And we located the tropopause around here, and the heating due to the presence of ozone in the stratosphere. So these temperature variations are called the lapse rate, and there are three types of lapse rates. The first type of lapse rate is called the environmental lapse rate, ELR, and this is what we did last week. It is the temperature variation with altitude. So it describes how actual temperatures vary with altitude, and as we saw, these can change from day to day or even over the course of the day, and these can be used to help with prediction when you see the changes. The second type of lapse rate is called the dry adiabatic lapse rate. Adiabatic is a pretty big word, one of those words you can use at dinner parties to impress your friends. It basically just means that a process, like rising air, does not exchange heat with its surroundings. And this is used frequently in atmospheric sciences. It's also used in studying other Earth processes, like the movement of magma through the crust. So the dry adiabatic lapse rate is the rate that the dry air will cool as it rises in the atmosphere. And this is a fixed rate of about 5.5 degrees Fahrenheit per 1,000 feet, or 10 degrees per 1,000 meters centigrade. And this diagram shows what happens at the bottom. You have 10 degrees, a parcel of air. As it rises up through the atmosphere, it expands and cools a fixed rate, 10 degrees per centigrade. So it's 0, then minus 10, and then minus 20. So this is the dry adiabatic lapse rate. The next type is the wet adiabatic lapse rate, and this is in particular application to the presence of clouds. So let's take a look at this one. So this is also called the moist adiabatic lapse rate, or the saturated adiabatic lapse rate. And it's the rate at which saturated air moves through the atmosphere. And we're going to use a value of 2.7 per degrees Fahrenheit per 1,000 feet, and you'll see other factors as well, but that's what we'll be using. And we use this type, or this lapse rate, to help describe air movement within a cloud. And if we bring our attention over here to the diagram, here is the dry adiabatic lapse rate of 10 degrees per 1,000 meters. And then once you get into the cloud, you switch, because the relative humidity is up to 100 now, you switch to the moist or wet adiabatic lapse rate of 5 degrees, and notice the change slows down. Now the reason why the change slows down is because during condensation, heat is released as a result of this process, which decreases that rate of temperature change. So it takes longer for the temperature to drop because you have a little heat in the atmosphere. So we'll be using this wet adiabatic lapse rate to understand a little bit more about cloud formation. Okay, so let's look at a few examples of how we use this environmental lapse rate in understanding the atmosphere. So here's a question. The environmental lapse rate is 3.8 degrees Fahrenheit per 1,000 feet. This is something that we measured through the radiosonde. If the ground temperature is 68 degrees Fahrenheit, what would be the temperature at 5,400 feet? And that value is picked out because that's the top. That's the difference between the Albuquerque and the top of the Sandia Mountains, which are right outside of Albuquerque. So we're going to use this equation, delta temperature. Change in temperature equals change in elevation times the lapse rate. So the change in temperature, we use 5,400 feet for the change in elevation, and here's the lapse rate. We're going to use 3.8, that was given, and you get a change in temperature of 20.5 degrees Fahrenheit. So we subtract that value, which I should have an F there, from the temperature at the surface, or at the base of the Sandias, and you get the resulting temperature of 47.5 degrees at 5,400 feet. So this is using a lapse rate that we've been given, okay, or that we measured using weather balloon data. So here's an example using just the dry adiabatic lapse rate. So let's take a look at that. So a balloon or air parcel of classroom air is 70 degrees Fahrenheit. If the balloon is brought to the top of the Sandia Mountains in Albuquerque, what will the temperature of the air inside the balloon be? Assume adiabatic cooling. So we're going to assume it's a dry bit of air and that it doesn't exchange heat with the surrounding area. So delta temperature, change in temperature equals delta elevation, change in elevation times lapse rate. We plug the values in using our dry adiabatic lapse rate to get the change in temperature of 29.2 degrees Fahrenheit. And so our new temperature is 40.8 degrees Fahrenheit. So let's look at an example now where we're using the wet adiabatic lapse rate. And this diagram over here will help us guide us through this process. Here is a cumulonimbus cloud. So a parcel of air is rising and expanding within the cloud shown to the right. At the bottom of the cloud, the temperature of the parcel is 55 degrees Fahrenheit. The parcel rises 3,000 feet to its new location as shown. And notice that the box is greater, so it must be cooling. what is the new temperature of this parcel? So delta temperature equals delta elevation times lapse rate. The change in elevation is 3,000 feet. The wet adiabatic lapse rate is 2.7, so we have a change in temperature of 8.1 degrees Fahrenheit, and so the new temperature at that height is 46.9 degrees Fahrenheit. Okay, so that is application of the lapse rate. I hope that helps with understanding the graphs, and I'll get to an example of that in a second. Now we can apply the lapse rate to understanding whether air is stable or unstable. Now, if you have stable air, that means the weather conditions will be relatively uniform, and you'll be expecting good weather. If it's unstable air, that's when you tend to have precipitation occurring and bad weather if you don't like precipitation, which in Oregon we all love precipitation. So let's take a look at examples of this. So if an air parcel is displaced vertically, either up or down, it will change its temperature due to the change in size, either expansion or compression. That's what we've seen in our gas law experiments, as well as looking at those past examples. An air parcel that is warmer than the surrounding air will rise due to its lesser density. So we also understood that from our experiments. And an air parcel that is colder than the surrounding air will sink due to its increased density. So that's just some basic physical processes in the atmosphere. So stable air is a term given to air that returns to its original position after it's displaced, either up or down. Whereas unstable air is a term given to the air that continues to move in the direction it was displaced. So if it's lighter and it continues to move, then it will be unstable and promote unstable weather conditions. So let's look at an example of evaluating stability. So here's the question. The environmental lapse rate this afternoon is 7 degrees Fahrenheit per 1,000 feet. This is in Albuquerque. A balloon of dry air is filled in Albuquerque. The temperature of the balloon is 70 degrees Fahrenheit. This balloon is then taken up to the tram. They have a big tram up to Sandia Crest, which is quite spectacular. Sandia Crest is 5,400 feet higher than Albuquerque. So the first question is, what is the temperature of the air inside of the balloon at the crest? So the way we do this, and I've just cut and pasted some stuff from some calculations I did, is we need to figure out the temperature on the inside of the balloon at the crest. So we figure out the change in temperature, and then we subtract it from its original temperature to get the new temperature. So 40.8 degrees Fahrenheit is the temperature of the air in the balloon at the top of the Sandia Crest. So question B is, if this balloon was released, would the balloon sink or rise? Now, first we need to calculate the temperature at the top of the Sandias. So at the top, the temperature is 32.2 degrees based on the environmental lapse rate. And what we need to do is compare the temperature of the parcel versus the temperature at the crest. Notice that it's higher than the temperature at the crest. So what that means is that the temperature inside of the balloon is higher, and therefore the balloon should continue to rise, and the air is unstable. So let's review those steps again. So first thing we need to do is determine the temperature of the air inside the balloon at 5,000 feet, and we did that just using the dry adiabatic lapse rate. The next thing is we need to find out what the temperature at the crest is, and we did that by using the environmental lapse rate right here. And our final analysis is comparing the temperature at the crest and the temperature in the air parcel. So this is warmer, so it's going to continue to rise, and therefore the air is unstable. So let's move to another example, and in this case we're going to be using a graph of the environmental lapse rate, similar to what you made. I've made this one much more simple, or Mel Strong did, so that some of the jogs are not let's see, what should I say? They're not distracting. So this is the sounding for the area that we're interested in. And here's a question. A balloon of dry air is filled at Albuquerque. It is taken up to Sandia Crest and released. Will the balloon rise or sink when released? Is the air stable or unstable? Let's take a look at the steps. And once again, I just cut and pasted some stuff here. So first of all, we can read right from the sounding that the temperature in Albuquerque at the base is around 74 degrees. We get that from the sounding. Now at the crest at 5,400 feet, the temperature is approximately 50 degrees Fahrenheit. So we grab that right from the graph. So the balloon will be at 44.8 degrees Fahrenheit when it's taken to the crest, which was calculated using this. So 74 degrees starting temperature minus the change in temperature equals 44.8 degrees. Took a shortcut right through here. Now, since 44.8 degrees is less than 52, the balloon will sink back toward Albuquerque, and therefore the air is stable, which means nice weather. So that's it for this almost 13-minute presentation. I hope this helps in terms of finishing the questions for part 1, exercise 1. Now exercise 2, which is about lapse rate, thermals, and cloud formation, I think it's pretty straightforward because I walk you through a lot of the steps, so it's the stuff that Mel did. Now, if you have questions, please put them up on the discussion board, and I'll try to be more attentive this week about those. And the only other thing to remember is that when you get cloud formation occurs when the relative humidity is 100%, and that occurs when the temperature, the air temperature, equals the dew point temperature. So I hope this helps, and thanks a lot.
You have learned that air that is forced to rise will expand and cool, and air that is forced to sink will compress and warm. These are the adiabatic processes. An air parcel is held in an equilibrium by two forces: the gravitational force that is trying to pull the air parcel downward, and the buoyancy force that is trying to pull the air parcel upward to the region of lower air pressure. Air that is warm relative to the surrounding air will rise due to its lower density. Air that is cooler than its surrounding will sink due to its higher density. Stability of the atmosphere is a concept that refers to the tendency of the atmosphere to either promote or inhibit vertical motion. Specifically, it refers to the tendency to promote or inhibit further free rising of air which has been forced to rise initially by convection, convergence, orographic lifting, or frontal lifting. During unstable conditions, air that received this initial kick to rise will keep rising further on its own account. During stable conditions, air that received that initial kick to rise will not rise further. The ball on a convex, concave, or even surface illustrates the concept. You have unstable conditions when an initial kick to an object will result in further movement. You have stable conditions when the initial kick to an object will result in that object getting back to its original position. You have indifferent conditions when the question whether the movement will go on depends on other factors. Atmospheric stability can be determined by the comparison of adiabatic and environmental lapse rates.
Is less than the moist adiabatic rate. When this atmospheric condition occurs, the unsaturated air inside a lifted parcel will be colder, heavier, and more dense than the air surrounding it. So when the parcel is released, it will fall back to its original position.
Stable air resists vertical movement. Stable conditions will prevent a parcel of air that was lifted from rising further, because the density of the air within the parcel is higher than the density of the surrounding air. Stable conditions prevail when the temperature of the air parcel that has been lifted is lower due to adiabatic cooling than the temperature of the surrounding air. Atmospheric stability prevails when the environmental lapse rate is small. It cannot be larger than the wet adiabatic lapse rate, which is approximately 5 degrees Celsius per 1000 meters. In that case, it does not matter if the air is lifted dry or wet adiabatically, as the temperature of the air parcel that has been lifted will always be lower than the temperature of the surrounding air. Again, at any stage, the temperature of the lifted air parcel is lower than the temperature of the surrounding air. So there is an ongoing tendency of that air parcel that has been lifted to sink back to its original position. We have stable atmospheric conditions. We start lifting an air parcel that has a temperature at the surface of 25 degrees Celsius, just like its surrounding air. We have set the environmental lapse rate to 2.7 degrees Celsius per 1000 meters. Notice that this small environmental lapse rate will result in a steep dashed environmental lapse rate line on the right diagram. As we start lifting the air parcel, the air will cool down first at the dry adiabatic lapse rate and later at the moist adiabatic lapse rate. At any stage, the temperature of the lifted air parcel is lower than the temperature of the surrounding air. As a result, the air parcel would have a tendency to sink back unless we force it to go further up. These are stable conditions. The increase of temperature with altitude in a part of the atmosphere is called a temperature inversion. A temperature inversion is an extreme case of absolute stability. The temperature of a lifted air parcel will always be lower than the surrounding air in a temperature inversion. It will therefore always have the tendency to sink down to its original position. An inversion layer near the ground prevents vertical mixing of air pollutants and traps them near the Earth's surface. Temperature inversions are frequent on clear nights when radiation is cooling the Earth's surface.
When this atmospheric condition occurs, the air inside the lifted parcel will be warmer, lighter, and less dense than the air surrounding it. So when the parcel is released, it will continue to rise away from its original position.
Unstable air promotes vertical movement. Unstable conditions will cause a parcel of air that was lifted to rise further freely because the density of the air within the parcel is lower than the density of the surrounding air. Unstable conditions prevail when the temperature of the air parcel that has been lifted is higher despite adiabatic cooling than the temperature of the surrounding air. The air will continue to rise because of its own buoyancy. Absolute instability prevails when the environmental lapse rate is higher than the dry adiabatic lapse rate, which means it needs to be larger than 10 degrees Celsius per 1000 meters. Under these conditions, it does not matter if the air is lifted dry or wet adiabatically, as the temperature of the air parcel that has been lifted will always be higher than the temperature of the surrounding air. Absolute instability is often produced by strong surface heating. Again, we start lifting an air parcel that has a temperature of 25 degrees Celsius. This time we have set the environmental lapse rate to 15 degrees Celsius per 1000 meters. Notice that this results in a rather flat dashed line on the right diagram. As the air parcel is beginning to rise and is cooled first at the dry adiabatic, later at the moist adiabatic rate, its air temperature is always warmer than the temperature of the surrounding air, which means that it will have a tendency to rise further because its density is lower. These are unstable atmospheric conditions. Conditional stability or conditional instability prevails when the question of whether an air parcel will rise freely depends on the question whether condensation is involved in the initial lifting. It occurs when the environmental lapse rate is between the dry adiabatic and wet adiabatic lapse rate, so between 5 degrees Celsius and 10 degrees Celsius per 1000 meters. The atmosphere is stable with respect to an unsaturated parcel of air. So a lifted air parcel will have the tendency to sink when it is lifted dry adiabatically, as you can see in the lower part of the atmosphere on the illustration. The atmosphere is unstable with respect to a saturated parcel of air. The lifted air parcel will have the tendency to rise when it is lifted wet adiabatically, as you can see in the upper part of the atmosphere on the illustration. In this example, we have set the environmental lapse rate to 8.7 degrees Celsius, which is smaller than the dry adiabatic, but larger than the moist adiabatic lapse rate. That results in a slope of the environmental lapse rate that is between the two adiabatic lapse rates. As the air parcel is lifted and cools at the dry adiabatic rate, its temperature remains lower than that of the surrounding air. That resembles stable conditions. However, as we cross the lifting condensation level and the air parcel cools at the moist adiabatic rate, its temperature all of a sudden becomes warmer than its surrounding, and therefore we have unstable conditions. We call this conditional stability or instability.
A conditionally unstable atmosphere exists when the decrease in air temperature with height falls between the moist and the dry adiabatic rate. A conditionally unstable atmosphere may become unstable if a rising air parcel becomes saturated and a cloud forms. The latent heat released inside the cloud warms the air to the point that the rising air is now warmer and less dense than the air surrounding it. The cloud will continue to build until the rising air inside the cloud becomes the same temperature as the air surrounding the cloud.
This is Dwayne Fred.
In this video, we're going to learn about tropical cyclones. The first thing you need to understand is that tropical cyclones originate over oceans in tropical areas and coastal regions. If you all know, this is the tropical region. It is the region of the earth near to the equator and between the Tropic of Cancer in the northern hemisphere and the Tropic of Capricorn in the southern hemisphere. Tropical cyclones are known by different names depending on the region. In the Indian Ocean, they are known by simply cyclones. If you go to the Western Pacific side or near the South China Sea, it is called as typhoons. Likewise, near Western Australia, it is known by willy willies. All these are different names refer to the same type of storm. You must be knowing this, that tropical region receives the most solar radiation per area, and the reason behind that is due to the incoming solar radiation that are direct and vertical at the tropical region. And as you move towards the polar region, the angle of the sun rays are not vertical, they are slanting rays. Vertical rays of sunlight are more effective in producing light and heat than slanting rays, and that's why the tropical region is warm. Now that you have understood the main things about the tropical region, let's understand about wind movement. Wind movement is determined by low pressure and high pressure systems. It is the differences in atmospheric pressure that creates pressure gradient and makes the wind move. And wind always blow from the areas of high pressure to low pressure areas. Now the next question is, what causes low pressure and high pressure? Low pressure occurs when air is warm, either from being over a warm land or ocean surface. That means low pressure occurs at a place which is warm. And how does a place become warm? Because of the incoming heat from the sun. That is why tropical region is a perfect place where low pressure occurs. Similarly, high pressure occurs when air is cool, either from being over a cool land or ocean surface. That is why in the polar region, that is your north and south pole, it is a high pressure zone. And always remember, winds blow from the areas of high pressure to low pressure areas. While all of this happens, there is another important phenomena which comes into the picture. It's called Coriolis Force. Due to the rotation of the earth rotates towards the east, and that's why the sun, moon, planets and stars all rise in the east and go towards the west. Anyways, due to the rotation of the earth, there is a force that is generated, and it acts perpendicular to the direction of motion and to the axis of rotation. In simple terms, when the earth is spinning in its axis from west to east, and we also know that earth is a sphere and it is much wider in the middle. As a result, the speed of the surface of the earth at the equator is much faster than the speed at the poles. So if anything has to come straight from the poles towards the equator, it gets deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And this force that we are talking about is called Coriolis Force. It causes fluids like water and air to curve as they travel across or above the Earth's surface. Due to Coriolis force, the air in the northern hemisphere gets deflected to the right side. Now you might think, no, that is going towards the left side, but then I said the air is going to curve to the right side in the northern hemisphere. To clear your confusion, you have to actually see it from the direction in which the wind is moving. So what I'm going to do is, I'm going to rotate this picture and now put yourself in the path of the wind. Now you will be able to see that the air in the northern hemisphere curves to the right while moving from high pressure to the low pressure area. Similarly, in the southern hemisphere, the air is deflected to the left side while moving from high pressure to low pressure area. In this case, we don't have to rotate the picture. Now that you have understood why the air moves to the left and right due to Coriolis force, just remember this point, that it is because of this reason there are certain pressure belts all over the Earth's surface. You must be familiar with this picture, which shows global wind circulation pattern. You can see that at different latitudes there are different pressure belts. Their existence is simply due to the movement of air to the left and right due to Coriolis force. I hope so far you have understood the general movement of air. Now let's understand how does air turns into a storm and what causes the spinning of a cyclone. When you look at the movement of a cyclone, at the center of every cyclone or hurricane, you will find an area of low pressure, which attracts the cool air. Since we know that air moves from high pressure area to low pressure area, That means the outer area of a cyclone consists of cool air coming from high pressure area, which surrounds the central low pressure area. This region is called the eye of the storm or center of the storm. The low pressure region is a warm region.
हाँ प्रतीक